This extended integral question is from the Cambridge Maths Admissions Exam STEP that Cambridge Maths offer holders take, and this is question 7 of a pure section in 1988. And this question requires a lot of integral manipulation without necessarily having to compute any integral themselves. So starting off, we're asked to show that I is equal to this integral on the left. And throughout the question, looking at the limits is often going to be a good way to signpost what your next step is. And immediately starting off, since we're being asked to turn our limits from 1 to 2 into 0 to 1, we can safely assume x equals 1 plus u would be a decent substitution to start off with. And this will give us dx equals du. So now if we put this in, we have 0 to 1, and then we will have in the numerator 2 minus 2 lots of 1 plus u plus 1 plus 2u plus u squared, to the k in the numerator, and the denominator will have 1 plus u to the k plus 1, and then we'll have du. So simplifying this down, we get 1 plus u squared to the k in the numerator and 1 plus u to the k plus 1 in the denominator, which is what we were asked to show. Now, in the next part, suddenly we have pi over 4 in the limits, and then cos pi over 4 minus theta in the denominator. So clearly some kind of trig substitution has been done here. Your best hint, since 1 has been turned into pi over 4, it's safe to assume that a u equals tan theta will work here. So we have du over d theta equals sec squared theta, so du equals sec squared theta d theta. So doing this, we get 0 to pi over 4, and we'll have 1 plus u squared becomes 1 plus tan squared theta. And with the identity, we can say this is sec squared theta. And then in the denominator, we just have 1 plus tan theta to k plus 1. Substituting our du out, we have sec squared theta d theta. And now we can put that into the numerator, and we'll have 1 plus tan theta in the denominator. However, the expression we're asked to form is in terms of cos. And we can handle this just by putting our sec squared in the denominator, turning it into cos squared. So we have cos squared theta to the k plus 1, and our 1 plus tan theta to the k plus 1 in our denominator. So now it would be wise to combine these brackets, because then we can start moving towards getting the rest of that expression in. So we'll have cos squared theta plus cos squared theta tan theta, which is just cos theta sine theta. This is all to the k plus 1. However, since we have a cos theta multiplied by a cos theta in the expression, it would be wise to factor this cos out. So let's say cos theta times cos theta plus sine theta to the k plus 1. And now it looks like we're really close to our expression. But we just have a root 2, and something needs to turn into cos of pi over 4 minus theta. So, I see what we have, and I think the addition formulae would be pretty useful. If we expand cos pi over 4 minus theta out, we get cos pi over 4 cos theta plus sine pi over 4 sine theta. And cos pi over 4 and sine pi over 4 are both 1 over root 2. So we have 1 over root 2 cos theta plus 1 over root 2 sine theta. And what we have is essentially this multiplied by root 2. So we can say I is, from 0 to pi over 4, cos theta times root 2 cos of pi over 4 minus theta, which is what this part asked us to prove. Now, the next part has changed the limits. Now we have a 2 in front of the integral, and it's between 0 and pi over 8 instead. Now, pi over 8 is halfway between 0 and pi over 4, and the fact we have a 2 shows that, it'd be good to try and prove that the integral between 0 and pi over 8 is the same as the integral between pi over 8 and pi over 4. So to do that, notice that the denominator stayed the same. And the illusion that creates is that we've made some kind of substitution where nothing in the denominator actually changes. So a good substitution to make would be theta equals pi over 4 minus phi. So if we do this, we get d theta equals minus d phi, which won't end up mattering because we can swap the limits back. So we have I equals from pi over 4 to pi over 8, and we might as well just change this now because of the minus in the d theta, or other way around. And then we'll have essentially root 2 cos of pi over 4 minus phi times cos of phi. And nothing's actually changed because of this. Oh, sorry, I forgot the k plus 1 power there. So these are identical integrals. So we can say the integral between 0 and pi over 8 is the same as the integral between pi over 8 and pi over 4, which means we can also say that this is 2 lots of the integral between 0 and pi over 8, because either way we're getting the same amount of area. So, moving on to our next part, you see that we essentially have the same thing as the first part, or really the second part, but the limits are different and we have our 2 in front. So clearly we do something to the integral we have now to return it to the first step while introducing these limits. Now, pi over 8 has turned into root 2 minus 1. But I think the main hint here is the fact that we've undone the previous substitution. Undoing the previous substitution will get us straight back to our second step in the integral, which was u equals tan theta. So to undo this, we would say phi equals arctan of x. And you can do the algebra, but this will take you straight back to this. And I'll leave out the upper limit for now, because that's the most interesting part of this part. So we will come back to what we had in this step. However, we have root 2 minus 1 in the upper limit. And the most important part now is showing that arctan of pi over 8 is in fact root 2 minus 1. So say tan of pi over 8 is t. By our double angle formula for tan, we can say tan of pi over 4 equals 2t over 1 minus t squared. Now, we know tan pi over 4 is 1, so we have 1 equals 2t over 1 minus t squared. You can tell now we're going to be working with some kind of quadratic, so let's expand this. We have 1 minus t squared equals 2t, and so 0 will equal 2t squared plus 2t plus 1, minus 1. So now, using the quadratic formula of minus 2 plus or minus 4 times 1 times minus 1 all over 2. So t will be minus 1 plus or minus 4 plus 4, so root 8. Root 8 is 2 root 2, so 1 plus or minus root 2. So either tan of pi over 8 equals minus 1 plus root 2 or minus 1 minus root 2. Clearly, it does in fact equal minus 1 plus root 2 by our limits. However, how do we justify this? Well, if we look at the graph of tan, it will look something like this until pi over 4, sorry, this is pi over 2. Okay, I guess I should have made it a bit more asymptotic. Anyway, pi over 8 will be somewhere around here. We can say that tan pi over 8 is positive, so we know root 2 is around 1.41, which is bigger than 1, so tan pi over 8 must equal the positive solution, which is root 2 minus 1. And that justifies us using this current integral. So now we have just two more things to show. Well, I guess one more. So we have this. Deduce the following. Now, it does look pretty similar to the original integral. However, we will also be using the current integral we have now. So taking a look at maybe the first part, we have 2 minus 2x squared plus x to the 4 over x squared, and then a 1 over x at the side. The 1 over x is a result of some kind of substitution we make, and the limits are pretty much the same as the original limits. However, it's 1 over 1 to root 2 instead of 1 to 2. So clearly we've done some kind of rooting here. It would be safe to go with x equals y squared as our substitution. So x equals y squared for the original integral. If we do this, we can say 1 equals 2y dy over dx out. Well, I guess I should have done the other way instead of implicitly differentiating, but dx will equal 2y dy. Now this is looking promising because when we put this in, we'll get somewhat closer to what we need. Essentially, I will be equal to 1 to root 2 of 2 minus 2y squared plus y to the 4 to the k over y squared to the k plus 1. And this is times 2y dy. Now we want to get this 1 over y on the side. However, we can then say, well, yeah, so the denominator is y squared, and this is to the k plus 1. However, see, we have the entire thing to the power of k in the final answer. So clearly we're going to take this y squared slash x squared out to make room for that 1 over x at the side. So we can just do that. We have 1 to root 2 of 2 minus 2y squared plus y to the 4. We've taken 1y squared out, so we can say that's k, and that will just be times 2 over y dy. Now, the actual question said 1 over y, but we can just take this 2 out to the front, like this. All we're really asked to show is that these two integrals at the end are equal to each other. So looking at this next one, we have 2 minus 2x plus x squared over x to the k times 1 over x. Similarly, we have 1 and root 2 as our limits. And the best way from here is to use the penultimate integral we had in this third line here, the one with root 2 minus 1 of the limits. And looking at these limits, we've turned root 2 minus 1 into root 2. So our best move here would be to do a substitution that goes around x equals y minus 1. So if we do this, I will be equal to 2 because we're using the previous integral. 2 lots of 1 to root 2, and then we have y squared minus 2y plus 2 to the power of k. Actually, I should do this. And then we'll have y squared to the k on the bottom. And this will be equal to, well, I should write dx equals dy here. And we'll have a times 1 over y as well. Just by taking the, where is it?
just by taking out the one of the powers here. So it's really ideal that we had that 2 from the penultimate integral, because then we have the 2 here and the 2 here, and we can in fact deduce that these 2 final integrals are equal.